Vectors, matrices, and all the things we can do with them. What really are these words? And why do we care about them so much? What operations can I apply on these objects? And why do we call them linear transformations? Let's explore each concept one step at a time, and by the end of this video you will have a solid foundation of this topic. We will then end with a question that is sure to get you scratching your heads, but more of that later. We start by looking at a simple vector. A vector has a direction and a magnitude. On the screen, you can see the vector 3, 4. This means that it goes 3 units to the right and 4 units up. To find the magnitude, we square each individual component, add them up, and then take the square root. We can also add one vector to another vector. Take the vector 3, 4 again, for example. If I want to add it to the vector 2, negative 1, all I do is I simply place the tail of the second vector on the tip of the first vector, and we have a new resultant vector. To find this new vector, we can simply add the x components together and the y components together as well. This is called vector addition. And also, writing the vector in vertical form basically means that the first number is the x-coordinate and the second number is the y-coordinate. We will come on to subtraction later, because surprisingly, we need to look at vector multiplication first. Multiplying a vector by a number, known as a scalar, can either increase or decrease the size of the vector. If we multiply by a positive scalar, we simply multiply each component of the vector by the scalar and get our resultant vector. However, if I multiply the vector by a negative scalar, something interesting happens. The vector goes in the opposite direction and also changes the length. This is because a negative number can be written as negative 1 times a positive number, and multiplying a vector by negative 1 is essentially rotating the vector by 180 degrees, as each of the positive components get mapped onto negative versions respectively. Now we come back to vector subtraction. Subtracting a vector can be considered as adding a vector, but multiplied by negative 1. So now we once again place the tail of the second vector on the tip of the first, but now we change the direction of the second vector. This gives us the vector that we need. One important thing to note is that you can only add and subtract vectors with the same dimensions. So for example, you can't add 3, 4 to just 5, as this is not defined in linear algebra. Yes, you can add it to 5, 0, but you must specify the 0, because in linear algebra, 5 is not the same as 5, 0. You might wonder what is so special about multiplying and adding vectors. But what if I want to multiply a vector by another vector? Let's stick to 2 dimensions for now. You would assume if this is your first time seeing vector multiplication, that you would end up getting another 2-dimensional vector. Well, you would indeed be correct, but you have to be careful how you orientate the vectors. The rule is as follows for any generic a times b vector multiplied by a c times d vector, where the first number is the number of rows and the second number is the number of columns. You can only multiply them together if b and c are the same number, and you will end up getting a vector that has dimensions a times d. So, taking our previous 2 vectors, arranging them both in the form 2 by 1 will not work, as 2 is not equal to 1. But as soon as you orientate this first vector to be a 1 by 2 vector, you end up getting an answer. But wait, I multiplied 2 vectors and I got a single point? This is not a vector, remember, as it doesn't have both direction and magnitude. You see, the thing is, vector multiplication is basically a mapping of one object to another, may this be a vector, point, or a curved surface. On the screen you can see some of the transformations, and we will come to these a little later. But first, how do I multiply 2 vectors? It's very simple really. You multiply each row of the first vector by each column of the second vector. You continue this process until all the columns of the second vector have been multiplied by the first row of the first vector, and repeat this process until all the rows have been multiplied. It will be more clear very soon. Now I know you saw the word matrix a few seconds ago, so let's talk about that. Simply put, it is a collection of vectors. And this is way more interesting to us because now we can do so much more with multiplication. What happens if we apply the matrix to the vector? And I say apply because all that means is you multiply this matrix by the vector. Apply is the word I use because I want to instill in you the belief that all of this is a transformation. So I multiply the first row of the matrix by each component of the vector, and I sum the numbers we get. This is the first coordinate, and I do the same with the second row and we get the second coordinate. So essentially, this matrix has transformed the vector 2, 3 to the vector 13, 8. But take note of this matrix, as every matrix will change every vector in different ways. For example, if I apply the same matrix to this vector, we end up with another vector, But this vector lies on the same line as the original vector. It is almost as if I have multiplied this by a scalar, but clearly I have not. I leave you to ponder over this and why this happens, and this will lead us into the beauty of eigenvectors and eigenvalues, known as the jewels of a matrix.